I'm very happy to welcome today Fernando Pereira, who is probably needs no introduction, but I'll say a few words anyway. He did his PhD at Edinburgh back in 1982, and I know some of you know the Warren abstract machine for interpreting semi-compiled Prolog. So his advisor was that Warren, David Warren. So he started out doing logic programming and made his way into NLP by way of, I guess, the parsing as logic connection, and did, in fact, some of the early work in agenda-based parsing, and did a lot of stuff in NLP. Then from there moved into machine learning, including machine learning for bioinformatics. He was head of the machine learning and IR department at AT&T Bell Labs, which produced a lot of wonderful people, including you could argue David Urowski and me. Both of us were there before we went to grad school, he after AT&T, he was chair of the computer science department at Penn, and he's still officially a faculty member there, but he's on indefinite leave because he's research director at Google in Mountain View. Have I left anything out?
Yeah, no, nothing there.
So all the good people work in his group. So.
Yeah, I don't know about that, but well, there are lots of Hopkins graduates in the neighborhood, which is great.
As I said, all the good.
Yeah, it's really nice. So I have a couple of minor apologies. So this talk is a variant of a talk I gave at the MNLP not so long ago. So if you were at MNLP, you just can walk out now and go and eat the rest of the cookies. There are a few new slides, but not that. The other thing is that it overlaps to some extent with, I know that my student Mark Dretz was here this morning giving a talk, and so some of what I'm going to talk about, he talked about. So the advantage there is that he gave you a good introduction, so I can be less clear about it now. So I can show some complicated equations a little bit. So what's the motivation? Oh, by the way, so the main new work here is joint work with Mark and with Kobe Kramer. Kobe has been a postdoc and research scientist at Penn, and he's just about finishing his last year there. He's on his way to be faculty of the Technion in Israel in the summer of 2009. Mark is about to graduate and is in the job market, as you know. And some of the earlier work that I will allude to was done with John Lafferty, Andrew McCallum, Ryan McDonald, and a bunch of other collaborators in sort of smaller ways. And it was done at the University at Penn and funded by DARPA and NSF in a variety of ways. So some of us have been using these boring linear models for classification for a long time, and why is there anything new to say about them? So I'll contend that, in fact, we don't know anything about linear models, and we're using them all wrong. But before I get there, let me tell you a little bit my view of history. So linear classifiers, you just take some object like a document or a context in part-of-speech tagging or a parsing decision, and you represent that object as some vector in high-dimensional space, where high could be very high, like millions in some cases, or tens of millions, and I've come across more than that. And then you think of a classification as separating the good points from the bad points by some kind of hyperplane. And if the dimension is high enough, and you are kind of lucky enough, you can find always a separator. But sometimes that's not strictly necessary. Say for documents, for text, often the features, these features, the coordinates of your vector are, for instance, the occurrence or count of a certain n-grams. There are lots of possible n-grams in English, so in document classification, if using trigrams or so, it's easy to get to millions of words, millions of features. Now, the linear classifiers are very attractive because they pretend that they use your geometric intuition. What's so hard about having, good points, bad points, and a little separator as a line? It's so easy to show in class. Everybody understands that. Now, there's a small problem that none of us understands anything above 3 dimensions, I don't think. I certainly don't. And even 3 is a bit challenging. And when you talk about million-dimensional problems, maybe our intuitions are not quite right. Now, the other thing to note is when you go to these very high-dimensional spaces, maybe your features, say, in this case, are n-grams. The statistics that you use to create these models may become a little bit bad. Most n-grams you see only a few times. They don't occur in most documents. So it's not so clear what we can conclude from the occurrence of those n-grams, or even worse, their absence. So regardless of these concerns, this has been a very popular line of application in NLP. So all of you, I'm sure, certainly have used Maxent models for classification in NLP. This became very popular work at IBM in the late 90s, 96. There's papers from the IBM group that were extremely influential. At the same time, more or less, people like Dan Roth and others started using other ways of building linear classifiers, this Winnow algorithm, which is a multiplicative update algorithm. I won't talk about Winnow because I don't really understand it so well. And then a little bit later, support vector machines, which had been developed separately concurrently during essentially the late 80s and early 90s, started being applied to text quite widely. And in particular, Thorsten Hopkins did some very influential implementation of support vector machines and application of text classification. At the same time, some of my colleagues at AT&T, Yoram Zenger and Rob Shapiro, started using AdaBoost for document classification, also with fairly good results. And both, even though these types of models seem different, they all eventually produce a linear classifier. Then in 2001, some of us started looking at applying linear classifiers not to the problem of binary classification or n-way classification, the discriminating good structures from bad structures in tasks such as part-of-speech tagging and parsing and so on. And one of the things that I want to speak about a lot during this talk is ideas about regularization, about smoothing in linear models, which I call regularization follies because I believe there's a lot of misinformation in this area. And I'm probably being as responsible for this as anybody else, but I've been trying to learn a little bit. And so that will be my emphasis. How do I do with sparse statistics in the context of these linear models with very high dimension? Let's see. So I'm going to kind of be a little bit tutorial for a few minutes. I know this will be boring for some of you, but just to set some notation and language and so on. So the Maxent classification idea in particular is all of the form of modeling the conditional probability of some label y given some instance or observation vector x. And this is parameterized by some weight vector w. So this is sort of the typical form of a Maxent model. And underlying to certain classification, so if I'm looking at the case of binary classification, I can actually go further back in history, and instead of thinking Maxent models, I think about things like logistic regression, where I think about some linear discriminant function h, which is a function of some weight vector w, and it takes x and produces an output value, an activation, positive or negative. If it's positive, I say good. If it's negative, I say bad. And the general idea for training such models is to adjust w in that case, you might say, I want to maximize the probability of observed training examples, that is, actual labels assigned to actual feature vectors. Or in a case like that, I might want to say, I want to minimize the classification error of my hypothesis H on the examples that I was given. And these are not quite the same. They may be converted to be the same under some distributional and Bayesian assumptions, but I won't go into that now. But in fact, distinguishing between that case, thinking about maximizing probability, and minimizing error can be important in practice, because of course your data is never drawn from a distribution of that form. So the standard, again, sort of a little bit of review. So there's a standard way of converting this story, the linear discriminant function story, where this function, so it's a linear, it's some weight vector dot product, some feature vector applied to my instances. And sometimes in this talk, so for convenience, I will elide the feature vector and just think about the whole weight x as the vector features. Sometimes I don't. I'm afraid that in my mind I always think in terms of features for practical and implementation reasons, but my notation doesn't keep up with that all throughout the slides, I realize. But so the standard and old technique to turn that into a probability model is logistic regression. I pass that linear discriminant through a logit function, and which has that shape, and produce the probability of y, the sort of the positive label given the instance and the weight vector. Now, the nice thing about this story is that, and there's an old, so it's this kind of funny thing, by the way, just kind of as an historical aside here. It's striking to me, is that when maxent models started being used in NLP widely in the mid-90s, although there is a huge literature on training logistic regression models, basically there was no interaction between those two communities. And in fact, in particular, a lot of the work that this community did on regularization, on smoothing, was not very visible to the NLP community for whatever reasons, and not probably good reasons, but communities developed along their own ways, and so there's a whole bunch of theory and experimental work on training models of logistic regression models, but mostly on applications such as biomedical applications, where the dimension of the feature vector is fairly small. Whereas here we're talking about much larger dimensions. This may be part of the reason why the community that was thinking about these problems in the NLP world was not paying enormous attention to what the logistic regression community in statistics had developed. So for training a model like this, you maximize probability of training labels again. And this is nice because it's a smooth convex optimization. You can go to your textbook and get to the good algorithm. But if you do that, maximize the probability of training labels, there are difficulties, for instance, for features that occur just, say, a feature that occurs just once with a positive example and never with a negative example gets a weight of plus infinity, which is not such a good idea, because it just essentially, if that feature appears, you know exactly what the classification is going to be, which may be kind of jumping to conclusions. So features, weights, that's sort of notation. So the conditional maxent model, which is sort of also called AKA multinomial logistic regression, although there's a slight technical difference between the two, it's the same story, except I may have multiple labels y. Instead of binary classification, I might classify into, say, different parts of speech. And it has a similar form where essentially this is a kind of softmax function, and you have to divide by some normalization. So this gives you multi-class address, and here the feature function applies both to your instance and the label. So in effect, what this leads to is the possibility that essentially there's a different weight vector for each label. Which, by the way, is something that's widely done, and it's not such a good idea in general, because it prevents you from sharing information across labels that might be relevant, although there are tricks with structured labels to address that problem. Anyway, so it's a useful notation. I think part of the reason why this became so popular in NLP, we have many multi-class problems like part-of-speech tagging, a classification into different document classes, and so on. And also allows us to kind of engineer different features, the different weight vectors for different classes. And training is still convex optimization, which makes it possible to use a toolkit of tricks to train in these models. And in fact, sort of these models have a beautiful little piece of the algebra goes very nicely. The gradient of the log likelihood of the data as a function of the weight vector is a difference between the actual frequencies of the features, the individual features for the training examples, and the expected number of occurrences of those features under the model you're training. So there's, at the maximum, that is the optimum, this quantity, the expected, the empirical average, of, the empirical count of those features is the same as this expected value. Now, another little side trip. For reasons I don't understand, and I actually once asked Fred, he's not here unfortunately, but I asked Fred, and he didn't give me a good answer, I don't think, and he normally gives good answers. Why did the IBM guys use iterative scaling to train these models and convince all of us to use iterative scaling? I still don't understand. Iterative scaling is a horrible algorithm. It's mathematically beautiful and numerically a disaster. So here's a little story of iterative scaling. Once upon a time, I was training some fairly large models, and they seem to be converging. But this is a time we started using, some of us started using different optimization techniques, LBFGS in particular, to train these models, and they were going somewhere else and say, oh, we have a bug in our LBFGS code, clearly. Well, no, we didn't have a bug. What happened is iterative scaling started, its learning rate got so slow, because iterative scaling is a method that has a nice property that's self-adjusting step size, which is great. Self-adjusting step sizes are really nice because you don't have to worry about line searches as you have for something like quasi-Newton methods. But because it's conservative to guarantee the self-adjusting, it eventually starts moving very slowly, so slowly that the increase in likelihood was below numerical precision. So he was going towards the objective, fine, but he was going at such a slow rate that we didn't see it. So that's a kind of an aside, but it's kind of a funny, yeah?
I was a summer intern in IBM in '94, so I might actually be able to shed some light on what happened.
Yeah, right. No, I'm curious. I mean, just historical interest, but it's like puzzling to me. But anyway. So the problem, as I said, is if some feature occurs only with one label and not the others, then you get this problem that the corresponding weight diverges to infinity. Clearly that's not what you want, because you don't want certainty, you just want somewhat high probability that label is is the correct label for instances with that feature on. So rare features get unreliable weights. So if a feature appears twice in one label and once in another label, is it really 2-to-1 odds ratio? Maybe not. Maybe it's 3-to-1 or 1.5-to-1, and we don't really know. If it appears 1,000 times in one label and 500 in the other label, maybe you could trust that statistic more. So the first idea, again, those of us who started using this stuff after reading the IBM papers, throw away low counts. Clearly, these features that occur these n-grams occur a few times. Why don't you just get rid of them? That has a very nice property, which is it makes the problem smaller, which the computers of back then was a great idea. But it's sort of a kind of a crazy idea, it turns out, because, there are lots, so suppose your features are n-grams. It's true that there are lots and lots of n-grams, most of which are relatively rare, but there are lots and lots of them. If you decide that you throw away all n-grams that are rare, you throw away most of your n-grams. And even them, each individually might not be very informative. Together, they actually may carry quite a bit of information. And we'll see examples of that later on in the talk. So a better idea, which by the way is the idea that the people in logistic regression had been doing all along, and we had forgotten to read up on the appropriate papers, said, oh, well, what do we now, there are various ways of thinking about this. There's a way that comes from optimization, and there's a way that comes from Bayesian statistics. The way it comes from Bayesian statistics is to say, oh, put a prior, and this is important for what comes later in my talk, put a prior on weight vectors, and then do something on the basis of the, essentially, instead of assuming that all weight vectors are equally likely, some weight vectors are better than others. Maybe, for example, you decide that a zero weight vector is best and put something like a Gaussian distribution on weight vectors centered at 0 and with some variance. Because you can't figure out what the covariance matrix would be, you just make it spherical and have a single variance coefficient sigma. Or it's called standard deviation there. So that's the way. And so then what you do is, so if you take this and you express it this way, there's this penalty on the log likelihood, turn into the log in terms of the gradient of log likelihood. You have your feature counts, you have your expected feature count according to your model, and here you have this penalty, which is the norm of essentially is you decrease your gradient by the size of the weight divided by this scale parameter. So this has some nice properties, right? In particular, if I have a feature that occurs a lot, then typically, so occurs a lot, it's one a lot, so the corresponding component of this vector is high. So that means that, let's suppose that this model is bad. So the corresponding component of that vector is going to be much smaller, because you get hit once for each training example. So this gap is big. So your gradient is big, even though unless the weight there is very big. On the other hand, if I have a feature that occurs extremely rarely, then what's going to happen is, the gap here is going to be small, because so maybe the number for that feature here is 2, and here is 1.5, and there's 0.5. So the only way to set that to 0 is to make the weight would have to be 0.5. So if the weight is 0.3, I still have some gradient and I move. So this formulation actually takes the frequency of features into account to some extent. The question is, does it take into account to enough of an extent? And this is what we'll get to later in the work that I did with Mark and Kobe. Just by the way, this observation that I just made is often ignored, because often people build a model like this, but instead of having the sums here, they have averages. See, notice this is the feature count. Now, this is the feature count, not the average value of the feature. This is the expected, and this here is the expected feature count, not the feature expectation.
So am I right that sigma square must be greater than 1?
Can be whatever you want.
Then
Greater than 0.
It can be. It has to be positive. Yeah, it's meant to be positive, but it doesn't need to. It's a scale factor, right? If you have a very small sigma square, basically this is okay. So the truth of the matter in these things is that people, what they do is just play around with sigma squared until things work held out data, so it fits reasonably well.
yeah, because you have Wn plus 1 minus Wn, and then you. It seems to me if sigma square is.
This is remember this is the gradient, right?
Yes. But then Wn plus 1 will be Wn plus the gradient, right?
The gradient can be positive, can be negative, right? You could be going uphill or going downhill.
What this is doing is subtracting, when you're updating W, you subtract some fraction of the current W, which pulls W back towards 0.
Yeah.
Yeah, but what I'm saying, if sigma square is smaller than 1, then you may not achieve that effect that one.
You're worried that it'll overshoot. I see.
Yes.
Yeah, it could. So I went over that. I didn't realize I had this.
Step size algebra.
Yeah. So first lessons. Count cutoffs were a great idea at the time, seemed at least a great idea at the time. And because of the reasons I said, small machines, slow training algorithms, like, given how slow iterative scaling was, and some somewhat simplistic views of overfitting. Better optimization methods support better regularization methods. You can, you have smooth optimization. You can use a variety of regularizers, including the simple L2 regularizer I showed you. And they need them. So here's another little observation. People that have worked in this area, not only in NLP but in statistics, say, oh, we need to optimize really well, right? So we're going to use the best possible optimization algorithm. And I won't name them, but they know who they are. Maybe they are not in this room. But the fact of the matter is, being optimal in this optimization is a two-edged sword. You're going to really try to capture everything there is in the data, even, of course, what is in the data just by the virtue of it being a sample from your, which may not be quite what you want. So very high demand, this optimum in very high dimensions is extremely sensitive to sampling accidents. So you need to regularize, Basically, so here's something that, going back to the iterative scaling story. When people are using iterative scaling from accident models, they didn't typically penalize them. Why? Homework. Why didn't people penalize their iterative scaling? Come on. Come on, it has to be one of the students. Come on. No, you guys all know the answer, I'm sure. No takers? Because it never got there. It was so slow, it did early stopping. It never arrived to the optimum. So it regularized by virtue of incompetence, which is a different kind of regularizer.
I don't think that's wholly true. So
Wait, I've observed this in reality.
It depends on the it depends on the particular problem that was being tackled.
Yeah.
But I can tell you that, for example, when Rhonda Parkey in 94, 95 was using iterative scaling, he used cutoff specifically in order to avoid the problem of weights going up to infinity.
Right. But let's suppose.
And he claimed that, just like cats back off, people say we don't have to regularize, we don't have to do any smoothing for counts that are over 5. Edward took the same.
I know.
Took the same position. Said, well, it's
I reproduced
there's
this.
enough balance.
I reproduced his work, so I know that well. So, but the count cutoff story for avoiding the weights going to infinity is just half of the story, right? Let's suppose no feature, all features occur in all labels. Even then.
No, you have to make sure that there's class balance between them. I mean, it's not as simple as a count cutoff.
Yeah, but the point is, if you do that, you find in many cases that iterative scaling will eventually, it goes very fast at the beginning, but then it becomes so slow that essentially you decide to stop it because you've been for 100 iterations, you can't wait any longer, and at that point, you essentially still far away from the optimum. And you can test this easily by having very, very weak regularizers without something like LBFGS, which is a quasi-Newton method, and find that in fact you get, you can get overfitting in a very, and the regularizer plays a lot of, you can actually do it's fun to do the experiments, by the way. I wish I had a lot of notes on these that I have never written up, but it's fun to actually try to understand what happens closer to the optimum. Which we typically don't do because we are working for conference deadlines. Now, norm-based regularization, like this L2 regularization, but maybe not enough, and we'll get to that in a minute. So, structure classification. I'll just do the tour because it's important for the rest of the story, because that's how I got to think about this. So people were doing things like part-of-speech tagging or parsing back around year 2000, they love to do generative models. So I have a stochastic process that generates my structure. And then basically classification is finding so I have my generative probabilistic model parameterized in some way, and I find the y that maximizes the joint probability of the input and the label. Here the label, of course, are many possible labels, many possible parse trees. Now, many other people are sometimes saying, oh, we have all this machinery for classification, like support vector machines. These are really cool. They really seem to work very well. So I want to do parsing of support vector machines. How do I do that? Well, I think about the first word. I don't know what to do. So I say, and this is, in fact, Ratnapark's parse. It works along these principles. I essentially do a shift-reduce parse, say, for recursive parse. I look at the first word, I don't know what to do. Look at the second word, I still don't know what to do, so push them onto a stack. Look at the third word, I still don't know what to do, but now I look at that and say, oh, I can combine these, and can decide to combine these. This is a binary classification decision, whether to combine, to shift or reduce, basically. I reduce and combine with the previous word, and reduce that, and I'm done. So basically what I'm doing is, at each step, I'm looking at the input, I'm looking at the previous parsing decisions, and I'm deciding the next parsing decision. And this is a classifier, and I can use support vector machines or max-n classifiers or Winnow, whatever I fancy. And indeed, people did a lot of work on parsing along these lines, some of which has been very good. And in fact, at the present time, now, the most accurate dependency parser I know right now for a variety of languages is built this way. So there are good news, and neither of these two approaches worked extremely well, though. The generative model, like HMMs, the probabilistic grammars, you need to have this generative model, which is a complete representation of the statistical relations you're interested in. So when you have features that are non-independent, for instance, in parsing and part-of-speech tagging, you have features like word endings and the features like lexical features, words belonging to certain lexical classes that are not statistically independent. Say, words that are end in ed are maybe more likely to be verbs. And as a result, these models have limited in what they can express. On the other hand, the sequential classification approach, you can use whatever features you want, whatever combination and fantasy idea of what features should be. But the problem is that once you make a decision in the past, and this is maybe not a good way to go back in this. Sorry, I shouldn't want to do that. Once you make a decision in that over there, you basically cannot anticipate what's going to happen later. Your decisions are sort of short-sighted. Just look at what you've seen in the past. And this is something that on a paper on conditional random fields we call the label bias problem, although it's an old idea that Leon Bottou had discussed in discriminative training for speech recognition in his thesis in French back in the early 90s. He never bothered to publish it in English because it was an obvious observation, but what's obvious for Leon is not obvious for the rest of us. So what we did was say, hey, linear classifiers are good. Why don't we generalize them to this problem? So rather than saying get the sign, so now I have some feature function f that assigns feature vectors to pairs of an input and a structure y, and I'm going to find the highest scoring choice of structure. And because going over all structures is a combinatorially hard problem, I want my features to be nicely organized, so I make the features the feature vector over the whole thing is a sum of feature vectors over a bunch of local domains which are just look at some subset of the structure, some bounded amount of the structure. So in the case here, part of speech tagging, I might have my local domains consider 2 successive labels, part-of-speech tags, and 2 successive words. And here in the case of parsing, I might say that each local domain corresponds to a subtree, a local subtree. And so because in practice, because I started building these feature functions that look a lot, and I have many types of local domains here, for instance, different kinds of words, different kinds of parts-of-speech tags, and so on. The number of, and this is why this is relevant to this talk, the number of rare features that arise can be very large. And I'll give you an example in a couple minutes. And just kind of some notation that I'll use later, or at least I want to introduce this notion that many of you are familiar with, but I remind you of the margin. So if I have x, which is my input, and 2 structures or labels y and y prime, then I want the score advantage of y over y prime, this difference here, you call the margin between y and y prime. And intuitively, the bigger the margin, the better my model is separating these guys, this y from y prime. So if y is good and y prime is bad, I want this margin to be large, positive and large. If y is bad and y prime is good, I want it to be negative and large in magnitude. So that's the general idea for thinking about margin. So there's a lot of theory relating margin to the online learning rate for online learners, like perceptron, for relating to good generalization for batch training, theory of the perceptron, the support vector machines, of AdaBoost, and many other classification methods, all based on the idea, this margin quantity. And it's all good to have this theory because we feel comfortable that someone is looking after us. And a nice thing, an observation I like to make also is that once you think in terms of margin, you can play also using the margin in different ways of measuring the quality of what you've done. So the standard log loss, which is the log of the probability of y given x, can be expressed in terms of the margin as written here. The Hamming loss, which says I want to minimize the mismatch adjusted misclassification. That is the number. So if I have some d, which is the distance, essentially a mismatch distance between structures. This, for instance, might be the Hamming distance if it's part-of-speech tags, say y and y prime in the 2 part-of-speech sequences. Might say how many part-of-speech tags are wrong in that assignment. And that's quantity. If this amount is greater than the margin, then this is a positive. If this amount is less than the margin, then meaning the margin is a strong separating y against y prime, then this quantity is 0. So basically, this idea of engineering a loss to satisfy your needs is an idea that's very natural in the margin setting, and it's not so natural in the probabilistic setting where you're trying to maximize probability. So margin, but you can also think of margin as some kind of log odds ratio, and in that way, the 2 things relate to each other. It's just people normally don't think of it that way, but it's a useful idea to have. So given this sort of margin-based these ideas, and one thing that now, let me give you a little bit of bracket here. So these structure models, what happens is in something I don't have a slide for, which I should have, I realize, is when I'm doing this calculation here, I'm sorry, where I went too far again. This thing, going back in Keynote is a bit weird. I don't know why. Sorry. When I'm doing this calculation here, even though for features based on local domains, I can do dynamic programming to find this y hat. This is still a complicated computation. So now if I'm trying to optimize to doing training, say, by using LBFGS or something else for a model like this. So suppose I'm doing minimizing log losses and maximizing conditional probability of the y's in the training data. I have each iteration, I have to run this algorithm to find the y hats that optimize the best y hat, or I need if I'm doing this, or I need to actually get expectations, which means I have to do something like forward back or an inside outside, And those are complicated computations. Say if this thing is doing parsing, say it might be n cubed, or for dependency parsing might of certain kinds. It might be n to the fifth if you're doing lexical ASCII parsing. Even for part-of-speech tagging, even though it's linear and with some back constants because of all the part-of-speech tags. So this calculation is slow, relatively speaking, and is in the inner loop of doing the optimization. Which means that sort of say if I apply something like some quasi-Newton method that has to do line searches and so on, you do many calls to this subroutine, and therefore your training is very slow. Sorry. So Mike Collins is sort of around, I think I don't remember exactly when, but it was just 2002 or so, something like that. He kind of had seen the work we had done on conditional random fields. He said, this is too complicated in terms of training. I'm going to do this very simply. There's this thing called the perceptron, which he had been doing a lot of work on linear classification with Yoram Singer and Rob Shapiro. He had a really good understanding of the theory. And he got the idea of essentially applying a generalization, the perceptron, to the problem. The basic idea of start some weight vector of 0, and then I go over the training data a number of times. For each training example, I classify the example, I incur some loss, and I update W to reduce that loss. That's basically what perceptron does. And there's some details of how he did it, but that's not relevant to this talk. Now, there's something that's slightly better in general than perceptron, and this is what Kobe Kramer did for his thesis, and which we used at Penn very successfully and others elsewhere. Instead of doing update W to reduce L, we are what Yoram Singer called passive aggressive. I don't know why I call it that. I know I actually do, but I won't tell. Which is if I am not if I'm already classifying sufficiently correctly, I do nothing. Now, if on the other hand I'm classifying with not enough margin, I am going, or classifying incorrectly, correctly with not enough margin, or classifying incorrectly, I am going to do enough to classify correctly with a minimum margin that is allowed. So how do I do this? It's the same algorithm schema, but one way to think about is, so for structure classification, I have some weight vector W, and I'm going to update it. So I'm looking at example I. Unfortunately there's a subscript I missing there, xi. I've used this picture several times, and I always miss some subscript. There's xi, yi. So what's the margin of the correct structure against some candidate incorrect structure, according to some candidate weight vector W prime? Well, I want it to be more than the distance, say the Hamming distance, for example, between y prime and y. That is, I want the correct one to be better than the incorrect way by at least as much as this distance. So for part-of-speech tagging, if I have a 20-word sentence and I make one error, so I'm less worried about that mistake than if I make 20 errors. And therefore, so for one error, I have a 1 here. For 20, I have 20. So if the case of 20, I want this difference in score to be much larger. So I'm going to find the W that is that is the minimum over all possible competitors Y. Yes?
So I have a historical question. Who is it who first proposed having the margin be proportional to the loss when you've got a whole bunch of competitors that you want to be? I associate it with Ben Taskor, who did it.
No, There's actually there are two concurrent efforts. Yeah. There was the work, and in fact they have different updates. There's the work of Thomas Tsokantaridis and Hoffman in the structural SVM. Yeah. And they have a scaling by the number of errors, but it's not the same scaling as this. This is closest to Tasker's. But it's not quite the same. Tasker uses this thing called the loss augmented max, which is a different story that I won't go into. It's actually the connection between this, the relationship between these things are like kind of a bit controversial, because if you talk to secondaries and all, they say, we thought it all before. My interpretation, they didn't. In fact, the loss augmented max and this sort of version of it is different. Now, there's some really wonderful work, recent work, that really clarifies all of this in a way that I wish I had thought of, which I'll mention in a minute. But it's just I'll give a citation, and I recommend that ICML paper from this summer that really puts it all to rest and clarifies it in a way that I think is very, very impressive. And it's by none of the people mentioned. Yes?
What if you don't have any W prime that satisfies that requirement?
Okay, so very good question. So if I have many y's, of course, these might not be separable. It might not be such a way. So there are two things I can do. Number one, I can, instead of having a strict separation, I can use a slack. So I can use optimization with slack variables. That's one way to do it. In fact, there's one way to think about it is to move this and, to take the constraint and put a Lagrange multiplier and move it into the objective, making an unconstrained optimization with a slack and a multiplier, which basically gives you a way of adjusting how much you give up on each example, essentially. So that's one way to do it. Which another way to do it is to say, hey, there are lots of y's. Just choose a few of them. In fact, just choose one of them. The best, the highest scoring runner-up, basically. And in practice, I've never seen that work much worse than anything else more complicated. Maybe somewhere there's one case in which I'll mention in a minute that I'll do. So I should hurry up because this story has many pieces, and I can get distracted. Dependency parsing. So Ryan McDonald and I and Kobe did this work on dependency parsing a few years ago, where we're learning how to do dependency parsing using around 7 million features, which is a fairly large problem, and you have to do parsing under the decoding. And the only point I want to make about that is I like this work, but so Ryan, for the insistence of his committee, they said, oh, you should do analysis of which features are important, and he went to dutifully do that. And the answer is, yeah, you can cut features a lot. Look here, this is 10 to the 5th, right? So 60,000 features, basically, I can achieve almost the same accuracy as 7 million features. Not quite the same. And this is through count cutoff and then some information gain feature selection method. First, they don't quite get there, and you know that in parsing, people care about distances like that for some reason. And the other one is that it never gets better. Now, people think about count cutoff as being good for regularization, or information gain as good for feature selection, say, oh, this should be overfitting horribly. 7 million features. How could you possibly live with 7 million features? Well, they seem to be doing fine. So that's just a little lesson. These online methods really work. So here's some data from an unpublished work that we've been trying to put together for publication for several years. Here's things like this passive-aggressive method versus Ben Tasker's approach versus CRFs. Somehow, for this handwriting recognition problem, in degree 1 kernel, it's actually CRFs and these actually networks do much better. But when you go for degree 2, everything does roughly the same. In fact, this one does a little bit better than CRFs. These are equivalent. For NP chunking, I don't see much difference between CRFs and passive-aggressive. Average perceptron also does pretty well. For named entity recognition, average perceptron does a little worse than passive-aggressive in the distinguished CRFs. So, if you despair of having a really robust implementation of LBFGS, you can give up. The last stretch. Features, so things I want to observe about the structured prediction problems. There are features of different levels of generality. There are these features that are lexical, there are features that are part of speech features. And basically, we don't take into account the fact that some features compete and others don't. So if I have the feature, the part of speech is such and such, it's never the case that that feature is always as on at the same time as the part of speech is something else for the current word. They cannot be on at the same time. So they're not really competing. It's not that two features that could possibly be predictive of the outcome in the same instance, which and they also, and more broadly, there are feature correlations and correlations that none of these methods, regularization methods, cover. Then there's this question of using real value features, which I won't go into. The thing about the different ways of scaling the margin by the loss. This paper by Sarawagi and Gupta in ICML 2008 is wonderful. I really recommend it. When Sunita told me about this work, and I just said, "Oh gosh, why didn't we think about that?" And it's just one. If there's time for the question time, I'll tell you about it. There's something else I won't have time to discuss here. So, just on the side, there was this fashion for L1 regularization in linear models. Oh, L1 regularization is using L1 instead of L2 is so much better because it enforces sparse models. And sparse models are good for some reason. Now, no one, unless someone in this room that hasn't told me so far, has managed to use L1 regularization to improve in generalization performance. No one. I don't know anybody. So it's not about generalization. Well, it's useful for reducing the number of features you use, but machines are getting cheaper. So is that maybe important, maybe not? And one thing I really want to point out is sparse instances do not entail sparse models. There are lots of features that are rare, but they are informative. And then the other point is if I have models that are long-lived, useful features keep arriving, and we should. But the first time they arrived, they are very infrequent, so you should throw them away, right? Yes.
So I do want to say something about bullet 2.1. Sorry, 1.
I didn't know them on purpose,
Yeah. It's true that you have enough memory to store the weights for 7 million features. However, extracting in for example, the McDonald and Pereira parser, which has been replicated here, all of the runtime is spent on extracting about 200 features per edge. The time for running minimum spanning tree and so forth is negligible.
Yeah, exactly.
Compared to the feature extraction time. So I think sparsity actually maybe is a good idea for not because of memory, but because of speed.
Franz Alko is your friend there for a reason. He argues that way too, and I buy that to some extent.
I mean, in terms of machine learning, I'm completely with you. I don't see any point in L1 regularization.
Anyway, so this L1 regularization is introduced in statistics as attractive approximation to sparseness, but to improve generalization, they thought, but it doesn't seem to help in NLP. So here's my made-up example that I like. I'm doing document classification to sports or unknown sports. I see football, and it's clear it's sports, right? I see curling. Well, it's actually it's probably sports too, but it's an L1 victim because there's not much curling in my corpus. I don't want to do that. There are lots of words that are weakly indicative of sports that together cover many articles. In fact, here's some statistics. In sentiment, some work that Mark is done in sentiment classification, log 10 of the count of the feature count, log 10 of rank. There are a lot of features on the top quartile of mutual information to the label. So these are useful features. Lots of them down there. So what we did, and this goes back to a bit overlap with Mark's talk, is say, look, we need to take into account this question that features occur with different frequencies, and some of them, we want to be explicit about the confidence in those features. So we took a leaf from Bayesian logistic regression and said, well, we're going to put a distribution over weight vectors. And I'm going to have a mean weight vector, and I'm going to have a covariance around that, and normally distributed weight vectors around some mean with some covariance. So that is going to be the way we manage certainty, or a useful way to manage certainty. So now the margin becomes a random variable. So it's the sign margin, which is the label. So I'm back to binary classification now. Y is labeled positive or negative, +1, -1. And this margin is now going to be a Gauss. Given that distribution of weight vectors, the margin is a univariate Gaussian random variable with this mean and that covariance. So now the probability of correct classification is given by the cumulative distribution of the normal cumulative normal distribution with those parameters, and as a result, I can do the following trick. So if Myra, the passive-aggressive algorithm, did something like this, here now I'm using a margin of 1 because I'm doing classification. I'm now saying, oh, this is minimizing the change in the weight vector, right? So I want to minimize the change in between these two models. Well, what's the minimum distance between two normal distributions, the decayal divergence? Such that the probability according to the new distribution of classifying correctly my current instance is greater than some confidence level, 95%, say. So now it happens that if turns out to do this minimization is kind of a complicated piece of nasty algebra that Kobe, fortunately, is good enough at these things to do. And there's a sort of a acute observation on the paper that's coming out in NIPS that if you, instead of using the covariance sigma, use the a square root of the covariance, then you can express the problem this way, where and this is where this is a positive semi-definite matrix, and in that form, this problem is convex, which so convex objective and a convex constraint, which is very nice because now I can apply all this sort of standard convexity algebra, in particular KKT conditions, to solve this explicitly. So here's now our new online algorithm. I initialize a mean to 0 and the covariance to essentially a diagonal covariance with some parameter a. I read an example with a label, and now I update the mean in some way where this alpha I here is some kind of variable learning rate. Why alpha I depends on exactly the classification of example I. And notice that for each feature, I'm going to, the update to mu for each feature depends on the covariance matrix at the moment. So what that means is that some features for which so let's suppose this is a diagonal covariance for the moment. So if a feature for which this diagonal covariance term is very high, then its update is going to be very large. Whereas if it's very small, then update for that feature is going to be very small. So if you compare that with perceptron, we're going to learn different features at different rates. Yes?
Do you want that to be an fi of x, or do you still?
Oh no, sorry, that's what I said earlier. I sort of dropped the f's to make the notation simpler. Yeah, sorry. Yeah. So, and then this is now with a full covariance. So this is an update to the covariance. Again, there's a parameter here, and there's outer product, the example with itself. And the effect here is that the places where, so suppose the x's are binary vectors. The places where features co-occur in this particular example are going to contribute to sort of decreasing the size of that component of the covariance matrix, basically. So this covariance matrix is going to be essentially in sort of the size of the eigenvalues is going to be shrinking monotonically, but at different rates depending on for different places of the matrix. Now I hid that stuff for good reason because it's kind of complicated and not particularly interesting. There's some parameters there. But I want to show you something here that's quite interesting. There's this big complicated algebra, but this term alpha, which is essentially the overall learning rate, is the interesting term here. It's kind of a maximum of these two quantities. This is so basically if something is correctly classified, then this is 0. If it's incorrectly classified, then it's some quantity here. Sorry, it's correctly classified with enough margin. It is 0. Enough margin to satisfy what we want in terms of probability. This is 0. Otherwise, it's some complicated quantity. What matters is this picture here. So that's the margin, 0 there. That's the alpha. It's very high if I get an incorrect classification. So we want to change this a lot. And it goes down. And the different lines are for different values of the confidence eta. So this one is for 50%. That's one from 99% over there. So basically, depending on eta, I'm going to more aggressively change for the update is more aggressive if eta is higher. So over there, for instance, I'm correctly classifying already with margin greater than 1, and I'm still updating.
0.5 is the hinge.
Sorry. This is 0. Oh, 0.5, yeah, it's a hinge loss, yeah. Hinge at 0, not a hinge at 1, right. So there this quantity beta, which has to do the update to the covariance, has sort of a different form, but the same thing happens here, right? If beta is 0.5, this thing doesn't change at all. The covariance stays the same, so that's the normal, this is simply stays the diagonal covariance. If I'm going to, so over there with high if the confidence level is 99% over there, then this amount is going to be fairly large even for positive margin, which means that this is going to shrink very rapidly towards 0, which means that my learning rate later on gets very small. So I'm going to learn very slowly. Whereas if the confidence is low, if I use a lower confidence rate, then the learning rate is going to be faster. And finally, I'll talk about, so let me just kind of get the diagonal covariance case. So this is, you project onto diagonal covariance matrices, so slightly different form here. But the important thing is this quantity here, alpha I over Si, also has a form like that. So this quantity is the amount by which I'm going to, essentially, I'm adding this amount. This is the diagonal square of the weight vector. So if this is a binary weight vector, it essentially tells you which features are on. These features are on. For each feature that are on, I take a scaling factor and add to the inverse covariance matrix and invert. So this essentially makes that particular component of the diagonal smaller. And the amount by which I make it smaller, again, decreases as I go to the positive margin, but it's not 0 at margin 0.
Okay. And this is presumably the one you actually do, right?
We've used both for small examples. For small problems, we use the other one that gets better results. For large problems, you can only use that one. So to visualize learning rates, so this is 20 features of which only 2 are informative in a shape like that. So this is the full covariance case. So after 20 feature, 30 rounds, 30 examples, you can see here the covariance ellipses for the 2 features, that the 2 significant features. It's very much like in that shape. And these are what the covariance ellipses for the noise features, the distractive features. So these are projections over two. These are basically ellipses that you project over 2 components. Now, so these are projected here over the right 2 components for that. So you see that you pretty much get close to the correct place very quickly, and you can change more in this direction than in this direction. Basically, your learning rate is pinned down that way. And for the diagonal covariance, of course, these things are axis aligned. These ellipses are axis aligned. The black one is on top of that. You can see it. This is the black and the green are the same after 30 rounds. So these are again for the distractive feature, for the pairs of distractive features. That's for the 2 meaningful features. So you see very quickly. You still allow yourself, for the features that are distractors that have no signal, their covariance stays very large. For those that are actually informative, the learning rate goes down very quickly. So you don't update them.
What's the red
The red line is that red. Sorry, this is sort of like, it's funny because this is sort of XY. This is just basically the separator that you are trying to get. So the effect of this is that this learns much faster. So the lines important. The lines I want you pay attention to are the red line here versus perceptron, the black line, passive aggressive, and there are a bunch of other things. But the interesting ones, I mean, we don't have time, is this one here versus that one and that one. So much faster, I'm getting no mistakes. So this is the rounds cumulative number of errors. So very quickly, I'm converging to a good model. This is on synthetic data. If you look at holdout error, again, this model that I just described, the full covariance case, and this is this one here. That's a different model that I want to talk about. This one here versus that one there. Clear. This is the diagonal one, which is not as good, but that's passive aggressive and that's perceptron. So in both cases, we're doing much better after a similar amount of work. In the real data, here is iterations versus the different accuracy for the different models. And again, ignore the CW var. So this is the one that I just described, this red line, perceptron, and passive aggressive. And no, this is one basically after 2 iterations, I'm where I want to be. Whereas here, I'm still learning after a while. And I think Mark talked about some results where you also, in papers, we compete very well with support vector machines and other batch methods for these problems. And so let's skip this one because it's difficult, maybe not the best one given we don't have that much time left. So here's 2 interesting pictures. One is log 10 feature count versus the variance for the feature. Rare features, basically rare features have still high variance versus the non-rare features. This is the negatives and positives. And here's mutual information between the feature and the label. It's kind of sparse. Most features have fairly low mutual information. But you see that basically, if I go to, there's sort of a cutoff there. If I didn't want to print lots more dots here, but basically, as I go into increase mutual information, the variance goes down as well. As you might expect, features that are very informative get lower variance. There's a lot more to do along this. So deal with feature groupings by maybe doing block covariance matrices, which we haven't done yet. But just kind of summarize the point of this thing is that sparsity and feature dimension are not really the fundamental problems here. The fundamental problem is how do we actually think about the features that matter and not matter in relation to each other, and how they interact with each other. And online methods are simple and always worth trying, even though not always the best. But the thing about which strikes me most is feature statistics. Why didn't we ignore it for so long? I mean, this is what's most interesting about the field, not NLP and different from NLP and between NLP and other areas. And even a simple model like this, which is just our first attempt at exploring systematically feature statistics, gets some very useful results. And I hope that continuing this line of work or related or competing lines of work, we can do much better in linear classification for NLP than we are doing now. Now, the problem even after that is that we still do not know how to discover effective features. After all of this, sure, I can learn given that you give me the features, but I kind of coming up with good features, good combinations of primary attributes of the instances to do classification. That's something that we still don't know how to do. We can do all sorts of hacks, but we don't really know how to do in a principled way. And that's all. Sorry, I went a bit longer than I thought. But.
Okay, thank you. Let's take a few questions.
Yeah.
In the 4 slides before, you had some equations, right? Like sigma i's.
Here?
No, the equations for sigma I and mu I, like some time back. Like,
Uh,
yeah, this one. So
you mean this one's here?
Yeah, this one.
Yeah.
So basically, mu I plus 1 is the iteration. I is the iteration.
Yeah, that's right. So this is like this is the mean weight vector. It's like it's an additive update, very much like a perceptron update, except that it has a variable learning rate in two ways. There's a sort of overall coefficient here, and then there is a per feature adjustment obtained through to the covariance matrix.
Oh, I see. So I thought that was a sum over
No, that's a covariance matrix. Sorry. It's the product of the covariance matrix by that instance. So if that's a binary vector, right, that's going to essentially scale the bits to bigger, fatter bits and thinner bits depending on the confidence you have in those features in doing that update. And that's the main difference between this and perceptron or passive aggressive, is that different features get their weights updated at different rates rather than having all of them updated at the same rate. And why that's important is because those that you have a lot of evidence for, that rate, their learning rate goes down very quickly. Meaning that, hey, I've seen this a lot. To change my mind about it, I better see, a lot of evidence. Whereas for features that are rare, I haven't seen much, so I'm willing to make bigger updates for them because for all I know, I was totally wrong. Which is a very natural thing to think. I mean, maybe this is not a natural way of expressing it, but it's certainly a natural thing to do. And what's natural about this is that by the magic of a convex optimization and matrix algebra and Kobe's late night algebraic calculations, we could get it to work nicely.
Do you still need to do this iteration many times for the data?
Typically a couple times. We don't need. I've basically after 1 or 2 iterations we're done for all the examples I've worked on. I don't know. Mark has done a lot more experiments.
2 versions. Usually, 2 usually does it as compared to perceptron. It's your right hand or something.
Yeah. Yes.
So have you applied this method to structure prediction problem?
Not yet. So it's actually a bit tricky. There's certain ways to think about it that don't work. And so the main problem is if I'm competing two models against each other, two weight vectors, two models which are, so if I have 2 weight vectors I'm competing against each other and computing a margin, that's easy, right? But here is 2 normal distributions, and if I'm computing the sort of this difference between them in that setting is actually hard. You get a non-convex problem, which is not so nice. There's a trick to do that is sort of an approximation that seems to work well, but we haven't explored it yet. It's kind of in our list to do. And the full covariance is not practical with a full matrix, really, for large problems. The diagonal covariance is practical. It's just one. Many people actually keep things like feature count in logistic regression, other kind of second factor for the weights in large linear models. So having an extra number for the diagonal case is not a big deal. Having a full covariance matrix, it's not, I think, practical. Whether we can do block covariance, other things like that is some to do. But the structure classification is clearly in a real to-do list. So the top against the other ones is actually relatively easy to do. Multi-class is really hard to do. We haven't been able to figure out how to do it well. We have an approximation that I worked out with Kobe like a couple months ago, but it hasn't yet been tested. Yeah.
In the case where you have, for example, millions of features, you mentioned the full covariance. So the reason you have a lot of complexity is because you have this multiplication of the covariance matrices there.
Well, you can do tricks. You can keep. Remember, you can keep some. Actually, we haven't fully worked that out, but I think you can use exploit tricks of maintaining a product of weight vectors and matrix in a sort of an incremental way that you don't need to do this full product all the time.
Because I see a product there for the update of the covariance matrix.
This, you mean this?
Yes, sigma and then the x.
This one here, right? Yeah, but there, I believe, by the way, I believe there's a trick to make this much, which is analogous to something that's done to update the sort of the estimate of the Hessian in quasi-Newton methods. I believe there is a trick to that way. Again, we haven't done it. But in any case, the big problem is the size of this thing. So if we use a reduced covariance matrix of some kind, then we might be able to handle large problems. But you have to see how to do this update efficiently.
Would that be the change if I permute the data, like the order in which it's read?
No. I mean, because it's still, even permuted data is still not the identity. I mean, it's still going to be, you would have to kind of renorm. I mean, you can't really even figure out what, you would have to do an eigendecomposition to get it into diagonal form. But at that point, you would have solved the problem that you were trying to solve originally. So it's not, there isn't no free lunch there.
But going back to Damianus's question, even if X was a 7 million dimensional vector and sigma was 7 million cos 7 million, in any given instance I.
Yeah. This is a rank 1 change.
Few components of X are non-zero, and so the update doesn't seem all that horrible to me.
You're right. It's more as this gets denser and denser as you go along. You start with the diagonal, right? As you do these steps, then it populates the off diagonal.
Just the storage of sigma is sigma becomes.
Yeah, and then computing this also. There are more components. There are more rows, right, in sigma I that become relevant because you're learning correlations between different features.
Yeah,
you're measuring correlation.
In the ith example, only some components of X are going to be non-zero. So you just need, in other words, you need fast access to sigma. But sigma being big doesn't seem to be a problem as long as X is sparse.
But notice that if I have suppose I have a million training examples, then I could imagine having the rows of sigma I become very large, lots of non-zeros.
Right.
That's the problem I'm a bit worried about.
No, but even if the row has many non-zeros, X has only 200 non-zero elements.
Yeah, that's right. Yeah. So I mean, I'm sure there are things to do with sparse matrices which I haven't done yet. It's all been done in MATLAB, mostly, or in Java, but not with any fancy sparse matrix implementation.
Probably maintain some sort of index of the non-zero elements.
Yeah.
Of sigma.
Yeah. I mean, there's a bit of a worry that you start getting all this kind of junk. I mean, the good thing is, I mean, in the synthetic data and the small data experiments, we haven't seen much evidence of overfitting, even with a full sigma, because it's kind of, and which is a bit of a character of passive-aggressive algorithms, because they are trying to do the smallest update. They are not, they are lower capacity than they seem. And so sigma looks like, you have n squared over 2 numbers, that's huge capacity, but it's very constrained.
No more questions. Let's thank the speaker.